So before starting any Cosmwasm project, these are the prerequisites that you actually need to have, which we actually discussed in the previous video as well. So first being Rust. So you need to actually have Rust up in your local system as well as the Rust compiler backend for Cosmwasm. Apart from that, you also need to have Golang just because you need to actually install binaries to interact with our testnet directly. So these are the core requirements that you will need before creating any Cosmwasm project. So let's move ahead. So for this workshop, we'll actually be starting by generating a bootstrap project from CW template, which you can just see here. So since we already have installed Rust as well as Cargo in our local system, these are the first packages that you actually need to have to in order to generate a CW template. So let's start with the practical examples. So we'll just create a new project right now. So let's start a new window. So the first requirement was install cargo generate. Feature was vendor SSL. And second was cargo run script. So these are actually pre-installed in my system, but if you haven't installed it, you need to install before running this particular cargo generate command. So we'll start with it. So first one is to install, like create, like generate a cargo CW template. So for this, we'll be just copying it. Let me just copy it. So for that, you can actually go to Cosmwasm template as well. CW template. So this is the Cosmwasm core repository where you'll file different templates, whether it's Cosmwasm NFTs or Cosmwasm templates or Cosmwasm plus contracts, where you will get to see more robust and highly scalable contracts as well. So here we'll just go to Cosmwasm template. So this is CW template. Here you will see all the instruction of creating a new Cosmwasm project from scratch. So we'll just use this with the project name. So I'll just copy this and I'll use a version of 1.0, which I already mentioned in my system, where we'll be actually having a core concept of a counter contract where we can actually understand how the states work, how transaction messages and execution takes place in a Cosmwasm contract. So let's make it as 1.0. And for the record, like this branch is an optional field. You can actually use any of the tags that you actually require for a Cosmwasm template. So, and I'll just rename this project as workshop 2. Let it be workshop 2. Okay. So I guess we are done with this, where we have actually created our workshop 2 based contract. So let's go and see how it looks. So we'll just go to workshop 2 and we'll open it. So this is the base structure of how a Cosmwasm contract looks like. So I'll be explaining all the components in details in this particular workshop. So let's start one by one. So there are many components in a Cosmwasm template, or should I say like a Cosmwasm project. So the first one is the dependency, then the entry points, then the state, error handling, event emissions, testing, as well as building and deployment. And these components are labeled in the sequence that way they are defined and in the sequence when they are worked upon. So let's start with one by one from starting. So first is the dependencies. So every every Cosmwasm or base, or say any Rust project has their own cargo.toml dependencies that they actually need to utilize to import any dependencies, any libraries they want. So in the similar fashion, Cosmwasm specifies, Cosmwasm also has this cargo.toml file, which is located on the root of the project, which actually helps you define all the dependencies you have, all the metadata you have, and any configuration that you require for a Cosmwasm uh, contract. So let's see where it's located right now. So here you can see that you will find a cargo.toml file. So let me just close this things. And here you can see you will find all the dependencies that are actually pre-installed here. And this is basically an optimizer. So optimizer, what it does is that whenever you create a wasm file, it is not always optimized. So Docker version of this Rust optimizer helps you create the minimal, or I would say the minimalist wasm file that you will actually be uploading into the blockchain through Cosmwasm. So this is the optimizer, and this is the library that you already use. These are the releases check that are actually followed while creating a release builds. And basically these are the versions and additions. So whenever we are actually creating some contract, we define some versions, and based on different amendments to that particular specific contract, and based on some changes in the code logic, we can re-edit different versions and create a migrations for it. So this is a quite brief introduction on how code.toml works and how dependencies actually work in Cosmwasm. So whenever we define a dependency, just the way you can consider an example that in Python we have a requirement.txt that has all the packages that are required for a particular Python file, and we run it by pip3 install my requirement.txt. The same way it works here, where you can just, after defining different packages that you actually require here, you can just write cargo wasm, which will actually build your complete project based on the requirements that you had and the whole logics that you have written. So it will be installing and compiling all the dependencies that we have actually provided in our dependencies. So while it's getting processed, we can go to our next slide, where we have entry points. So what is basically an entry point? So in every blockchain, a smart contracts need to have an entry point through which, like, the external agents or external actor, and who are those external actors? We, the user or developer, who can actually interact with that particular blockchain. So for that, we have entry points. There are quite a many entry points that can be associated with any smart contract. We have mentioned three major common entry points, though there are more and can actually work based on different use cases. So first is an instantiate. So in previous video, we had already talked at what is code upload. So whenever, like, we create a Cosmwasm project, we then upload it to a blockchain. But just uploading a code doesn't actually simplifies that it will run based on any transaction or something like that. It's just a code which has no instance as of now. Instantiate work at that particular point of time, where a external actor can just provide some initial parameter to a code and create a new instance for it. Consider it like a function is already provided in case of some Java or Python, but you have no objects written over it. But whenever you create an object on top of any functions or any parameters, then it creates a new instance for that particular object. So similar is the case with instantiate, where it creates an instance of that particular code. Users can create as many instances they like for a particular code as well. So there's no issues in that. And every code, or for every code and every instance, there will be a separate state associated with it. And so let's see how instantiate works. This source is supposed to be having all the core logic of a smart contract. So let me get to all the things step by one by one. So first is a contract. all the core logic of a smart contract, whether it's a transaction, whether it's to instantiate, whether to create a query, all can be written here, and is, as we can see, is already written here. Second is an error. Error is a file where all the expected errors that can be present in a contract are registered here, and based on that, we just use those particular contract errors in the place that we actually require. Helper functions are, you can consider those as some secondary functions that your contract might require by importing those functionalities in their contract file and then use it thereon. And it's completely dependent upon users or the developers of their how they actually want to place those helpers, like, and how they want to align their files. But the important thing is like how, where and all we define our entry points and the associated functions. Integration tests are similarly where we write all the test cases that are actually present there, in order to, so that when like all the test cases and all different functionality tests can be done here. And library is something where you already define like what all grades are actually, or what all grades are used, or what are libraries, or what are files that you are actually going to use. So for that you will be using library.rs. There are two common major thing between message.rs and state.rs. Since you know that we as an actor can has to interact with our blockchain through these transactions, or say instantiation, then we are the ones who will provide a message to a blockchain to execute a particular transaction. The messages file actually defines that what are the different messages we can expect from the user, and based on that particular message, contract execute its code logic. State.rs is something is where you can actually consider it as a storehouse of a blockchain, where all the states or any change in a parameter or any state change can be tracked here. So for example, you can see we have defined a state, which is an item, and which actually stores a struct of having a counter and an order. So we'll go more details of logics of this particular contract, but for overall view, you can just understand is like a state is where you will have all the variables, or the you can see the state variables associated with it to store the corresponding values. So these are the core structures of how Cosmwasm smart contract looks like in the SRC file. I'll tell you more about like what target 2 is, what a schema is, and all in the upcoming videos as well. So I guess so what we thought about is like instantiate is a entry point, execute is an entry point, and query is an entry point, and we can associate it as like this. Like in this contract.rs, you will see an instantiate which has an entry point defined over there. Defining an entry point allows us for the external actors to directly interact with these particular functions. You may define different function, as you can see that we have just defined a function called query count, which is actually used by some entry points, but they are not called directly. They are called through different entry points. So entry points are the places where you will actually be interacting with the blockchain, or any external actor will be interacting with the blockchain. So these are the entry points. So as we can see, like in our particular contract, we have an entry point of instantiation at execution, as well as in query. You won't find entry points anywhere apart from these three right now. So here is the entry point. State, as I already mentioned, that represent how the different data and variables are used in a smart contract, and are basically defined with different structures or data types, which can be either like string, boolean, custom types, enumerators, and many more. Now let's talk about error handling. So every time you execute a transaction, you either get a successful message stating that you have actually successfully executed the transaction, or there might be some failure points on which you will bound to get some errors. So error handling is the most important thing in all, where we have seen that can be many chances where there are errors but are not often detected at the testing, and the runtime it can actually cause issues. So error handling is the most important thing I would suggest in a smart Cosmwasm smart contract development. And thus, like, this one is event emission. So most of you who have actually hands-on Solidity must be knowing how events are. So whenever we actually execute a transaction, we try to log those events so that any external party which is outside the blockchain can see what actually happened in a particular transaction. So event emission is something that helps in that particular part, where upon executing a transaction, you will actually be getting to know that what actually happened, what are the variables you have actually executed, what was the event, and that is actually based on the requirement. So event emission works in that particular part. And last but not least, testing. Test cases are the integral part of a Cosmwasm contract, which can be written there. And test cases, like Cosmwasm, had different libraries to create a mock environment where people can just provide different use cases and different test cases, like test scenarios, and based on that, they can run those test cases. And the last is build and deployment. So once everything is done, we come off building, like we go with building a smart contract and then deploying it. So we'll see all the steps one by one in this current contract. So let's see like how the whole flow goes like. So this contract is actually a counter contract where an owner just triggers a transaction, and based on the transaction, a counter is updated by one. This is a very core example right now. In the upcoming workshop, once we are able to understand this contract carefully, we will be able to create our own NFT platform, or you can say our own NFT marketplace, where we will start with defining our own structures, our own states and messages, and how it actually works there. So for this bootstrapping project, I think like we should go with this. So let's start with instantiation, which is the first part of our contract deployment. So what happens in instantiation? You can see that upon instantiation, it has some states and some versions. So let's look at state and messages before jumping into any functions. So we can see we have a state where a state contains a struct having a counter or a owner. So you can understand struct in the similar way it's written in like how in C or C++. So there's no a big difference in that. And these are the different macros that are actually utilized on this particular state, where serialization, partial equation, like partial equaling of different components and converting into a JSON schema, and serializing, deserializing, and in fact, like cloning, where you can just create a replica of a particular state. So these are the macros that are actually supported in your state right now. So we'll talk about it in the future videos as well. So you can see that in the state, we have a count of integer 32 and an owner, which is the address. And you can see like Cosmwasm STD provides different data types as of now, and one of them is address right now. So, and a new variable is created. You can say it as state, which is a constant variable, and which is actually pointing to a state. So there will be only one instance of state which can keep on changing, but yeah. So this is the state, and this is the state that we are actually going to change every time. And you can just consider it a structure or kind of a schema through which the state is actually stored. And the second goes with messages.rs, where we have different instantiation message, execution message, query message. And you can see here key in the instantiation message, we are actually providing only a count, which is an integer 32. And execution messages, we have two enumerators. So enumerator is something like you can consider at it, like enumerator is kind of similar to what we use in Python as well, where you have different versions out of which you can consider one of the thing. So for say for example, like if you want to execute a message, you can either go with an increment or a reset. So that's how enumerator is actually used, where you can actually enter any one of the index of the different variants that you have in an enumerator. And similarly works in query, where you can have different queries and you can provide all the different variation of queries in a particular enumerator called query messages. And here we have a struct of count response, which is just a struct, so it doesn't have any states or any enumerator thing as or to have an entry point. So now let's understand how what instantiation is actually trying to do. So while instantiating, like it asks for some different parameters. So I'll get to all of them one by one. So depth is something you can consider as the storage of a blockchain where all the data are stored. Environment is kind of you can consider as all the it contains all the chain related data, like what is the block height and basically yeah, and like various balances or contract address it can actually have. So env helps in that. Info is something that is designed for message execution. So whenever you are creating a transaction and what all information are actually given to a blockchain in order to execute a transaction is provided in an info, whether who is the sender of that particular transaction, or be it like did he actually provide some funds or not, and what is the height, and everything is actually provided in this particular info file. Message is some external image, like is an external message that we have just provided right now. And you can see that in message.rs we have defined that in instantiation we just want to provide a count. So when a user provides a message of count, you can see that the message.count is all set in the state struct, and the owner and the one who is trying to instantiate is defined by info.sender.clone. So clone is something where you just create a replica of the whole sender. So it's to avoid like borrowing issues. So for that you can actually go through Rust and see how borrowing actually works in Rust. So here we have created a state struct where we have just defined a message count and an info.sender, and that is supposed to be provided by the one who is instantiating. So once any user instantiate a contract, he cannot run this transaction again for the same contract. Like he can run different instances, create different instances based on different instantiation messages, but for one instance, it is basically a one time run. And now we are actually setting a contract version where we are actually using workshop 2 as our contract name, and we are defining a contract package version. Contract package version is provided in the env, which we have already seen in our cargo.toml file. So the notion of using this contract.version is that whenever we are trying to migrate, or when we are trying to change any logic in an existing code, and then we are planning, okay, we need to just point to a particular instance to a new code ID. There we can define a contract version, and based on this contract version, we can define like whether that contract, if the contract version is above or below that particular previous contract, then only we should do a migration or upgrade. So there are code logics for that as well. So once we have defined the state, we'll just save this save struct in the save variable. So this is a way to do it, where we'll just point to the store that we are actually using. So deps actually uses a storage to store all the values that we are actually using. So in this part, basically we are storing this state struct where we have actually defined count as something that is provided by instantiation messages, which is actually provided by one who is executing this message. And the second is the executor who is actually executing this initiate message. Once it's actually done, we can actually see that the state is being saved and a response is created. So you remember that we had talked about that event emission, where once we have actually triggered some transactions, then after that successful transaction, user can see like what all things has happened. So this response is supposed to create an event emission. Our response is a result. So in Rust, a result has two enumerators, or not enumerator, I would say two variants. First is a response and or a result. In a result is it's okay or error. Means suppose if your transaction is completed, you will get a success message or some error. So we are actually bound to get any of the two from here. Say for example, in the set contract message, it can actually result in a standard error as well, where you can see that it gets a standard error where either a okay response can be given or a error can be given. So that's how we actually use a result, where it's not always necessary that okay we'll get a successful response, we can get a contract error as well. And our main aim will be to, and with this basically contract error actually works in a way where chain level panics can be just minimized by using like proper checkpoints on your contracts. So first, suppose we have actually used our instantiation message, where we have instantiated with our count and sender.clone. So for the time being, let's consider that the sender actually provide the count as 0. So the current state has a count of 0, as well as the owner is some address ABC. Now comes the execution message. So you can see that in execution message, we have all the three same parameters, but now this message has a type of execution message. And when we see execution message, it's derived from the message crate. And when we go to the message file, we can see execute message has two variants. First being the increment, and the second being the reset. So let's see how we handle it. So when we are actually getting message as a input for the execution field, we actually have a match, like we have a match functionality where we can actually match what that particular message was. So suppose if this particular message was increment, then we would go for this particular function and execute it. But rather, had it been this reset message, we should have gone to the try reset. So here you can see that in the message we had these two, you say like these two variants, and based on these two variants, we can just define that which of the flow that particular transaction can go. So let's try to understand like how increment works. So here we don't expect any arguments as such, as it actually just needs a storage. That's it. So once it actually goes to a storage, which is a depth mute. So with depth mute, depth stand for the like depth is the storage, and mute actually stands for the mutability of that particular storage. So you will often see depths as well as depth mute. So whenever there's a chance or there's a scenario of some mutability of a state, we actually use depth mute. And as often like we use the result, and in this result it can have a response as well as contract error, and based on this we will actually be creating a new state. So what this code logic does, it actually updates the state by 1. So here you can see that it actually creates we actually have a function associated with the state, which updates that state count by 1 and then return the state. And once this is completely done, we have an like okay response of the increment was successful. And reset is something like we just updated to a new value. So here's a check that the one who is actually trying to execute this transaction is defined by info.sender. Info is the parameter that tells you about the information of what all transaction parameters that have been provided to the blockchain to execute, and from there it actually tends to get the sender. So had it not, if it's not actually the owner that was which was actually set in the instantiation message, where we see that we had already set an owner, and owner was the one who actually triggered this instantiation message. So had it not been that particular owner, we would actually return an error. So these are the two variants that you will see. So, on the successful response, we just responded by okay, and the response type we have, and on error we have a contract error. So here see we have two variants of our response type. One is a response on successful completion of the transaction, and one is the contract error, which we define when we are getting when some of the checkpoints are not passing the criteria. Then we can simply define an error to restrict the transaction to complete. So basically these are the two core examples of how transaction of different states have been changed, where we have incremented the counter by one or resetted a counter with a defined counter item. Now comes second thing is query. So we are done with instantiation. We are done with messages, or should I say execution messages. Now the third one is the query part, where we will actually try to get the state variables and display as an output once the query, once the user or any external actor actually wants those particular data. So you'll see that the messages are query messages. As example, for querying, environment is provided and depths. You will see one difference is like on different transactions and instantiation, we use depths with the type of depths mute. But in query, you will see only depths. So I guess you must have figured out the reason that since we had talked about the mutability of our storage, so that's why we used to do depths mute. But since we only want to have a query on that particular any data, we are not going to change any variables or any state. So for that reason, we will only be using depths, not depths mute. So you can see in the messages in the query enumerator, we just want to get the count of a particular of whatever the count currently is going on, and we have only one enumerator variant of this particular enumerator. So similarly in the contract, you can see that we have a match message for the messages type that we have a query message. We can just check that, okay, once we get this get count message, we will just query the count and convert it to the binary. So it's kind of a serialization technique where you can just provide it's a better way of giving a response rather than any or any anonymous query with any given struct. So it's kind of a healthy way to write a query of first getting a query data and then converting it to a binary. So that's how you can see that the standard result actually accepts a binary as a query. So let's see what the query does. So in the query, you can see that first it tries to load the data. So you can see that whenever we defined a state struct or the state variable in this state, we can do two things with it: get the data or append or change the data. So you can see in this thing where we have in this try increment where we have actually updated the data, or you can say, let's say, saved the data. So basically state changes are actually done by these things. And once we are actually trying to just get the data, you will see that, okay, we have actually got the state data by using the load command. Load command will get you the data, but since you are actually using depths, not depths mute, so you cannot change anything in the state variable or in the state basically. So and now we actually created a counter response that you saw in the message, where we have a counter response. So the idea of using a counter response is that whenever you want to provide a query in a specific format, then you can actually provide the structure or kind of the struct of that particular requirement, and based on that you can just provide or just query those data in that particular sequence based on the requirement you have. So you can see here state we have got, and the state response, the count variable has been assigned with the state dot count, which we actually loaded from the state. So from here we can actually load the data and the response will be actually given. So currently we have actually covered instantiation, execution, as well as query. Now we will be going through how test cases are written and how different scenarios are covered in the test cases. So for test cases, we have to define a configuration of tests where we'll create a separate mod for this. And these are the different libraries that are actually supported by Cosmwasm STD for testing, where you can just mock dependencies and mock environment and info. So I'll brief you about why these test cases are required. Every time someone builds a Cosmwasm contract, it's not always like that they will be testing on chain. There might be no chain while developing, and there comes sometimes a hassle of every time creating a new contract, uploading it, instantiating it, then verifying whether your desired input and the current input are same or not. And this is kind of a tedious process. That's why we have mocking environment, where we have all the data that are required from the chain with the mocked values, and based on the mocked values you can just check whether you have your core logic or your contract logic is correct or not. So I'll just give an example of how. I'll just take a proper instantiation message only. So we talked about the mocking dependencies, where we create a dependency with uh, some tokens that are there that will be there in the contract instance. And then we have actually defined, okay, what is the instantiation message. So we must be remembering that in the message we had discussed that while instantiating a contract, the executor actually has to provide a count. So so for this mocking contract or the mocking test case, we have defined a message where we have provided a count as 17. And as you know, the info provides everything about the chain data and whoever like is actually working on it, what are messages that are actually provided to that particular transaction. So in this particular information, we know that the transaction is done by someone whose name is as creator. You can consider him as an address or as a name, but this is the creator right now. You can consider as a single entity right now. And what he has is he's providing some funds to your transactions, and his fund is 1,000 earth, and earth is basically a custom token that we have actually defined. So once we have created our info, depths, and messages, then we can directly use our instantiate messages, and we can just create this function. So in this particular function, we are creating using depths and using our depths as mute, called a mute, or basically a mutability feature of depths. We are using the mock info, where we are actually mocking an info. And whenever we are actually mocking an info, you can just go to the definition of how it actually works. Okay, we need to actually install it to actually know it. Which we can actually do later.